For the third part of our 1.2 notes, we're going to be looking at a concept called continuity, and we're going to see this both graphically and algebraically. So the definition of continuity from looking at the graph is basically being able to draw the whole function without ever having any gaps or breaks in the line. For example, this one has a removable discontinuity because there's a little hole punched out of the graph right here in this section. So I wouldn't be able to draw the whole line without taking my pencil off of the paper and then placing it back again on the other side of the hole. There's another type of discontinuity here where it's not just one hole punched out, but the whole graph gets kind of cut off and then separated. So again, I would have to remove my pencil from the paper at this point, move it up to this point, and then continue drawing the function. And then here's another case of discontinuity, usually caused by an asymptote, where if I was drawing this line from left to right, I would hit this point, put a little arrow at the bottom, and then I would have to take my pencil off the paper, bring it all the way up here, and then continue drawing from that point. So every time you have to remove your pencil from the paper to connect the graph to draw the whole function, that's a discontinuity. So continuous everywhere. Removable discontinuity, we're going to learn from the equation that means there's some way that we can get rid of that problem. So it's removable because we can fill the hole basically. Jump discontinuity, this is usually caused by something called a piecewise function, if you recognize that name. So usually it's actually two different functions that are defined for certain x values. So it causes a gap in the graph here. And then these are the ones caused by asymptotes. The two on the far right are non-removable discontinuities. There's nothing you can do to fix those discontinuities, while there is a way for us to turn this into a continuous function. The more common type of question in this class will deal with looking at the equations and figuring out whether it's removable or non-removable based on that information. So removable discontinuities are zeros in the denominator of a fraction that can be canceled out once you have everything in factored form. That's what causes the hole we saw in the second graph. So basically you're going to factor everything on top, factor everything at the bottom for your fraction, and then if you can cancel out the value that makes the denominator equal to 0, it's removable. If you cannot cancel out that factor, once you factor the top and the bottom of your fraction, then we call it a non-removable discontinuity, and that's because that value actually creates a vertical asymptote. So I'm going to show you examples of what this looks like. Sometimes it's easier to see the example and then look back at the notes to make sense of it. So here we're being asked, are there any discontinuities? And if there are they removable or non-removable? So the first step is to factor both the numerator and the denominator down. On top, I see that there's a GCF. Both of those terms are divisible by 7, so I can write this as 7 times x minus 2. In the bottom, I can actually take out a negative 1, because that would turn this into an x minus 2, so that we have matching factors on top and bottom. The fact that they match lets us cancel them out, so this whole function is just equal to negative 7. Now, if I was just looking at negative 7, I wouldn't think there are any discontinuities because I don't even have a fraction anymore. But if we remember that we had a problem up here originally, x couldn't equal 2 because 2 minus 2 would equal 0, and you can't divide by 0. The bottom of a fraction cannot be 0. So x equals 2 was a problem value for this function. The fact that we were able to cancel it out, that's what makes this a removable discontinuity. And I'm just going to abbreviate that here. So removable discontinuity. And then they want to know where the discontinuity occurs. It happens when x equals 2. Because x equals 2 is the value that makes the bottom of our fraction equal to 0 or undefined. So here's another example. Again, I'm going to start this off by factoring everything on top and bottom. On top, I see a GCF. Everything's divisible by 2, which leaves me with 2 times x plus 1. And on the bottom, this is a trinomial, and it's the easy trinomial. I don't have a number in front. So first two numbers have to multiply together to equal x squared, which means it has to be x times x. And then the second two numbers, the last numbers, need to multiply together to equal -5, but I need them to add up to -4. So my two numbers in this case are going to be -5 and +1. And again, that's because -5 times 1 equals the last number, -5, and -5 plus 1 equals -4, the middle number. That's what makes this the correct factorization. So here again, I see that I have something matching on top and bottom, which lets those two factors cancel out. So my final answer, this function, is equal to 2 over x minus 5. So again, looking at what cancels and what doesn't, that's how we determine the removable and the non-removable. So the removable discontinuity, just like on the last one, it's based on the value that makes the denominator equal 0 that can be canceled out. In this case, if x equaled -1, this factor would end up equaling 0. So the removable discontinuity is when x equals -1. The non-removable discontinuity is the one that can't be canceled out. So the non-removable discontinuity is at x equals +5, because if x equaled 5, then this other factor, x minus 5, would equal 0. So this one had two discontinuities. It has both a removable, which is sometimes called a hole in the graph, and a non-removable, which is usually an asymptote in the graph. Here's some other questions I could give you based on what you've already seen from the rules for continuity. This one wants us to state where the function is continuous. So basically you want to think about what x values you're allowed to have, or what is the domain you're allowed to have. In this first function, f of x, the only x value that causes a problem is when x equals 4. Because if I take the factor x minus 4, set it equal to 0 and solve, I find that 4 for x makes this function undefined. But every other number is okay, because our domain, we assume all real numbers for our domain. We only look for values that make the denominator 0, or we look for values that make the inside of a radical negative. So on this one, I just need to exclude 4. So the way I would say that all of the numbers except 4 would be starting from -∞ and going all the way to +4. And then I need to do a union because there are more numbers. There are the numbers that are bigger than 4 as well. So I also have from 4 to +∞. This is basically saying everything from -∞ to +∞ except 4, because I use parentheses to exclude that value. Here's another example that might be a little bit trickier, because the rule for radicals is that the inside of the radical, which is 2x plus 1, needs to be greater than or equal to 0. Otherwise, it ends up being an imaginary number, and we're not dealing with those right now. So when is 2x plus 1 greater than or equal to 0? Well, I can solve this just like an equation by subtracting 1 and then dividing by 2. So this function works as long as x is bigger than or equal to -1/2. Since I'm allowing equal to, I need to use a bracket to say -1/2. And I want the numbers bigger, so I'm going all the way to infinity. So this is where the function is actually continuous. It's where the function is defined for that second example. This slide isn't really about a type of question I would ask you. It's more about a term you need to be familiar with. They often use this terminology in the end of course exam made by the county. So I want you to know what a bounded function is. And I've given you the mathematical definition here. You would say a function is bounded if there's a number so that the absolute value of the function is less than or equal to that number. Now that's kind of complicated sounding, so I tried to break this down into an easier to understand phrasing. Basically, this is telling me mathematically that a function is bounded if it doesn't go up or down forever along the graph. So if there's some kind of a line, like an imaginary line, that your graph stays within, it's like coloring in the lines of a coloring book. So I see two dotted lines here and here. This pink function is bounded because it never goes past that boundary. The blue function is not bounded because it has this tendency to go up forever or down forever. So it's like it doesn't have a limit. It can go on forever wherever it wants. So bounded doesn't increase or decrease forever. There's some kind of a point where it stops going up or down. And then this is another definition, not really an example so much. So I have the mathematical definition here for something called the extreme value theorem. And it says that if you have a real function that's continuous, so there aren't any gaps or asymptotes in it, and it has a closed interval, so maybe we're only looking at the numbers from 2 to 8, and we have brackets on the ends, and if it's bounded, the same thing, then f must attain a maximum and a minimum at least once within that interval. So here's me trying to translate that for you guys to make it easier to understand. Basically, there is a highest and a lowest point of a graph of a function if you're only looking at a small section of it. For example, right here in this graph, it might go on and do lots of other stuff on either end. But if we're only looking at this part right around here, I can define a maximum and a minimum, which we covered in the extrema earlier in one of the other sections of notes. So if you have a bounded small section of a graph, there exists a maximum and a minimum within it. Here's another example of a closed off section. Now in this point, the maximum is still that location where the graph switched from increasing to decreasing. So the maximum was not one of the endpoints. But the lowest point that the graph ever hit can be found by looking at this end. Even though we don't have the decreasing switching to increasing, the graph still has a lowest point called a minimum. And then here's one more example. This graph is bounded because it doesn't go forever in any direction. We're just looking at a small closed portion of it between A and B. There is a lowest point and a highest point on it. You can see this within the little section I've drawn. So there won't be any examples dealing with this, but I wanted you to recognize that when you have a small closed off interval of a graph, you should be able to identify a highest and a lowest point somewhere within that interval. And that's all for the notes on this section. And in fact, that finishes all of 1.2 off. Thank you guys.